Okay, so here I want to talk a little bit about electrical resistance. Again, we'll just go for 12 volts on this power supply because it's usually quite nice to work with because it divides by 2, 3, 4, 6 and so on. And we've got a resistor here and a bulb. Now any component has got a certain amount of resistance. Anything in real life does. Again, like I said before in the previous video, with wires the resistance tends to be very low, so low we can ignore it. And I forgot to add an ammeter, so I'll put one of those in. And remember, that's measuring the current. So that is effectively measuring Q over T. Okay, so we've got this circuit set up, and let's just say that we've got a certain resistance for these both. So we could say that this is, I don't know, 10 ohms. And we'll say the bulb is 20 ohms. So what we can then figure out is what are the different potential differences across them going to be. Now, we've got a total resistance for this circuit, which when they're connected in series, that resistance just adds. So we've got a total resistance, we call that RT, of 30 ohms. Okay. Now, the resistance and voltage and current are all related together by the equation V equals IR. So the voltage is equal to the current multiplied by the resistance. Now with these, we've got those two components connected together and their total resistance. And if you remember, that voltage should be about 12 volts. So that means that 12 is equal to I times 30. So then what we can do, of course, is we can solve for I in order to get what the current is going to be. So I is equal to 12/30ths. We can just simplify that by dividing both by 6, which will give us 2 fifths. So that's just 0.4. We tend to get quite low quantities for current. So 0.4 amps, there we go. And that should be the same everywhere. Now, that means it is the same in each of those. So considering that, we can now find out what voltages are actually across these ones. For example, if I was to imagine connecting a voltmeter here and connecting a voltmeter here. So V equals IR. So for this one, well, the current is 0.4, the resistance is 10, so we get 4 volts. Same kind of thing, V equals IR, and that voltage, we're looking for current 0.4 times 20, which gives us 8 volts. And if you notice, two different things. These sum up to give this, of course, but also these are divided in the same ratio. So here we've got, this is 1/3 of the total resistance, this is 2/3 of the total resistance, and you can see you get 1/3 of that voltage and 2/3. So that's one important thing to realize, is that the potential difference shows us how much energy gets sacrificed in pushing the charges through those. So you can see it's easy to get through this one. It's more difficult to go through this one, and it's in that ratio. This is twice as difficult to get through, so it takes twice as much energy to push the charges through there. What we also want to look at in this case is, well, let's look at this in a parallel circuit also. I'll just rotate the paper around a bit so we've got some more space. So we've got a parallel circuit, and let's imagine, okay, so this time we've got a battery. Okay, remember, as opposed to a cell, which is one of those by itself. And then let's stick an ammeter here. And we'll put 2 resistors here. Resistors can fairly well stand in for any component. Any component can be treated as a resistor, depending on what we want to look at. It's look at what it's doing. Okay, we'll put, whoops, not the nicest diagram ever, but I'm sure you understand it. Okay, so again, we've got 12 volts up here. Let's give this a resistance of, I don't know, 5. And we'll call this 15. We'll call this 20. And we'll call this 30. So what we can say, of course, is that the voltage across these, and this is a parallel circuit. So we've connected the second branch. And what they should do is each branch should have the same voltage across it. So this should be 12 volts. And this also 12 volts. And this is why parallel circuits are very useful, because if we just added loads and loads of components in series at the home, for example, all you would get is each would get a smaller and smaller share of the total energy being transferred in. And so, every new thing you added would just cause everything else to get dimmer or be less effective. Whereas this, we add the second branch, and they get the same amount. Now what that implies is that it sucks more current, so it's going to drain the battery more quickly. because it's, it's draining the current, because the current is what's carrying the energy. So we've got an ammeter here, and I forgot to connect ammeters here and here. Now you will remember that the charge is conserved, so the charges get pushed by this, they go around, and when they get to this point, they split. Now how much goes into each branch depends on the resistance. We are going to get a larger current up here because there's less resistance. And what we can do is we can figure out this current here. So we'll call that I1, we'll call this I2, and maybe, oh yeah, so they travel around here, they get back to here, and they join together. So maybe call this IT. So we could say that IT is equal to I1 plus I2. Just another way of saying the current gets to this point, splits, some goes this way, some goes that way, and then they join back together at this point and then go back to this. So this tells us again that this is IT. Remember, we go with our conventional current going from positive to negative, as opposed to electron flow, which goes the other way. We use conventional current because we have to relate it to forces and things, and it's the rule that we've come up with, and it works just fine, even though it's not really true, but it doesn't really matter. So let's look at this branch. So we'll get I1 here, and if you remember, I is equal to V divided by R. So we can just get that, so that is 12 divided by 20. 12 20ths, I wish I had a calculator with me, but well, we can divide both by 4 to get 3/5, which is the 0.6 amps. There we go. And then, so by the same thing, so there's I1, there's I2. We can just get that the very same way. 12 divided by 50, because there's a total resistance, remember? There's resistance for both those. And that is going to give us, right, we'll divide that by, oh, no, hold on. Let's say it's 2400, so 0.24. There we go. I'm just doing this in my head, even though I shouldn't because I'm sleep deprived, but obviously much better to use a calculator. Just by this then we can get I total, which is going to be equal to just the sum of those two. So IT is equal to 0.84 amps. There we go. What can we get also? So by the same, well, we don't need to do that all over again, but we can get the share of potential differences. Now we can see here that this is a quarter of the total potential difference. So that should have 3 volts across it. And then we should get 9 volts across this one. This one is 2/3 of that total potential difference. 2/5. 2/5. So it's just the potential difference across this should be 2/5 of 12. The other thing I want to say is that what we can then get is the total resistance of this circuit. There's 2 different methods we can do that. So we can do that just using V equals IR. Okay, so we know that R equals V over I, and that means that the 12 volts divided by 0.84, that will give us the total resistance to this circuit. But the method you'll be asked to use more often is this. I'll show you this as follows. So let's just look at this network of resistors. So we'll take this, we'll sort of rip those out of the diagram just so we can look at them. What we essentially have is, we've got these 2 here. Those are 5 and 15. And this little dot just shows that it's connected, instead of just wires going over each other. And here we've got 20 and 30. I may soon wish that I'd chosen different numbers, but there it is. We can treat these as one resistor here. So we could even simplify this a little more. We could treat these as a 20 ohm resistor and treat those as a 50 ohm resistor. And so we get the total resistance. Now we use fractions to do that. You don't need to know exactly how until you get to A level, like how we get to this. But 1 over the total resistance is equal to 1 over R1 plus 1 over R2. So that's 1 over 20 plus 1 over 50. And of course, we don't need to worry about the lowest common denominator. We just do whatever common denominator is, which here luckily is just going to be 100 in hundredths. So, 1 over RT is equal to 5 over 100 plus 2 over 100, which gives us 7 over 100. And then that gives us 1 over RT. So we've got to do the reciprocal of this to get the total resistance. So that would be 100 divided by 7, which I'm sure I can't do in my head, but it's about 14. And what we see from this is we usually get a resist. That's supposed to be the omega sound, by the way. Let's just do that properly. And what we usually see is that the total resistance we get from this is much lower than either of the resistances here. As this gets larger, of course, this is going to approach this one. It's going to approach the this value here. But we can kind of think about this as that the electrons now have two different paths they can travel through. So it is less resistive overall because there's two different ways they can go. A resistor we can kind of imagine being like a narrow hallway that's difficult to get through. But if you've got two narrow hallways, it does become a little bit easier.